resources. So it's really great to be able to come and just talk a little bit about the types of models that I've been running during my PhD. I hope this is going to work okay. I'll share my screen and I'll run through some of the code that's on the GitHub now. The way I've set up this session is one of my hobbies is to find papers that I think, oh wow, that looks really interesting. I wonder if I can replicate that model myself. Yeah. And so what I've done a couple of times is I've gone away and you can extract a variance covariance matrix or a correlation matrix of means and standard deviations out of a paper, code that into R, and then you run the model. And then you can see whether you get the same results out. And in the examples that I'll show you today, you do get basically the same results out. Sometimes you can't make it exactly the way you see it in the paper because of different decisions that authors have made with putting various variables together mostly. But I've got two examples to show you, and one's from quite an old paper, which was written as kind of a demo paper of how you write and report confirmatory factor analyses for the literature. And then the other one is a recent paper, which was a structural equation model, but it built in like a time scale. So often in structural equation models, you see cross-sectional data. And I find that a bit problematic because of this idea of causal inference, that in a structural equation model, things are supposed to be causing other things. But even if you put variables at different ends of arrows, if you've only got cross-sectional data, you can't really like make strong causal claims. And one of the fun things I like to do with honours students at UNE is to demonstrate a mediation model, and you put the variables in this way and then just put the variables in the other way and it works. And you get these nice regression coefficients and they go, oh, how is this possible? And so, yeah, so the second example I'll show you is that one. And then at the end, I'll just show you some code for just the entry level, how do you code in a latent growth curve model? And so for that example, I've just actually lifted the correlation matrix out of my own paper, the one that Jenny found on the conversation. And so the results that we'll get out of that one won't be exactly the same, because in that paper, I did a group comparison model where you use measurement and variance tests to test whether you can equate parameters. And this one, I'll just do a general overall model and show you how you can code in a latent growth curve. So let's see, I might switch between screens a little bit. Let's see. Because I've got the examples on a PowerPoint presentation, and I'll just show you what the examples are. And then you can, at the end, I might be able to share this in the GitHub as well, because you can go away and find these papers and actually look at them if you want to. So this first one is from, I'll just scroll down here to the references. It's from this Schreiber paper, Reporting Structural Equation Modeling and Confirmatory Factor Analysis Results, from 2006. So it's quite an old paper, but it's got some nice diagrams in there. So the first diagram that I'll try and replicate in this R code is this one. And so it is a paper, it's got an education focus to it. And so the constructs that are there are deep learning, and then I think it's isolated learning. And they're indicated by, each of the latent factors indicated by 3 observed variables. And so this is what the model looks like once they run the model with the data. I'm just going to make this smaller so I can see what I'm doing here. And so what I did was I just took the correlation matrix out of the paper, and I'll show you how you can code that into R so that you can actually attempt these models yourselves. So I'll just go to my RStudio screen. Okay, so if you've been onto the GitHub, you should be able to see this syntax. And I've just got comments throughout just to try and help you out. I will be demoing the lavaan package, which I really like. And one of the reasons I really like it is because it's got really excellent documentation. And so even for me, a totally newbie beginner a couple of years ago, first attempting this, I went into that tutorial, which you can find here at this website. and worked through the tutorial, and it actually made complete sense. And that's really excellent, because sometimes the packages in lavaan in R I find completely uninterpretable, and I have to muck around a lot to figure out what they're doing. So I'm just going to bring up, if you haven't got lavaan already installed, you'll have to do install packages, and then just like that. I didn't put that in the code. Oh, there it is. It's up there. You have to unhashtag that and run that bit to make lavaan work. And hopefully that works. Sometimes, I don't know, sometimes I go to install packages on different computers and you have to do this crazy thing where you have to go into the site and download it. So if you have issues, yes, you just go onto the site and see if you can see why it's not working. Then I'm going to run through this. I ran through it last week, so I hope it's not going to all fall over on me and tell me my directory is wrong. No, so this is where I'm working from. Now, in these examples, I don't have data files that are actual numbers in rows. So I don't have like all the participants with all the actual numbers that represent those variables. But if you do, you just run this for CSV files or whatever type of file you have, SPSS files or whatever you use, and then just bring them into R. In this example, I've got my instructions there. What I'm going to do is I'm going to make make several objects, and then that's going to be the data to run this example. So basically what I'm doing here in this example, the variables are standardized. So the means are 0 and standard deviations are 1 for all of them. In other examples, I'll show you what happens if the means and standard deviations are not 0 and 1. And so basically, if I just run these, I'll get some objects and it will just be, they'll just appear over here. And then what I'm doing is I'm telling it to read the data here. This CSV file is just a correlation matrix. So it's got means, standard deviations, and correlations between all the variables. And then I run these. This is telling it to use this data matrix as the correlations. And then it's transferring the correlations to covariances. So this is just all what we're doing in the background. Oh, what's happening?
Finding those things, Sally.
Pardon?
It's not finding them for you.
Not finding them. I'm going to have to go and see. I'll just look in my folder. ELPB. I knew this would happen. You know, when you go, oh, I'll just run this and it will work like it did work before. And then it's not working.
Did you run your WD line?
Did I? Well, maybe I didn't. Maybe I didn't do that. I'll try that. Because it made my 2 objects, didn't it? Error. What's my error? I can't see it because of that. If this example doesn't work, I'll just try my other example because I know that example worked. And I'll have to go back and see why this isn't working. More columns and column names. I'm just going to scroll down because this is just a one standalone example, and I'll make sure, I'll see if this one will work. Why? Don't you hate that?
Oh, you totally do. Like yesterday it was running just fine, and then as soon as you are on Zoom with lots of people watching, it's like refuses to read any data.
So it's doing the same thing for all of them, and I don't know why that is. Shall we pause for 10 minutes and I'll go away and see if I can figure out why it's doing it? Do you just want to pause the recording?
Yeah, let me pause this.
Oh my God, what? I'm going to, okay. I'll just have to reshare my screen.
Okay, good plan.
Okay.
Yeah, the recording is going again. Problem sorted. You've got to run every line.
You've got to run every line. So that's the, that was the issue for those of you tuning in at home. I did not run this line. This line tells us what the variables are called. And so now I have run it, so it says names over here. And so now when I run this bit, I've already done that, but I'll do it again. It brings up this correlation matrix up here, 7 observations of 7 variables. Okay, and then I'm just going to run this bit, and that just transforms it into covariance matrix using the information that you've given it. If you have your own data, you don't need to worry about that section at all. So don't feel overwhelmed by that bit. That's just my hobby, is trying to run those sorts of things. Okay, so the first model that I showed you before was the 2 latent variables that were correlated. So 2 factors, each of them are made up of 3 observed variables, and they're correlated with each other. So it's a pretty simple sort of model. And so what I'm doing here with lavaan, there's several steps that you go through to use lavaan. So the first one is you define the actual model that you want. So in this case, I've got one latent factor called deep and one called ISO. And then these are the operators that you use, the equals and then the squiggly line whose name I can never remember. And it's made up of 1, 2, 3 variables. So it's really actually very straightforward to define a model. You go, here is my latent variable, and it's made up of this plus this plus this. And then here is my second latent variable here, and it's made up of this variable, and this variable. If you have more variables in your data set, that doesn't matter. So if you've got control variables, or you've got another set of data that you're not using for your given application, you just tell lavaan that you're just using these variables, and it's fine. It won't fall over. And so if we run that little section there, all it does is it creates model number 1 over here. So it's just a little object that you're creating. And then the next step in using lavaan is to evaluate the model fit and to also tell lavaan which data that you're using. And so that's in 2 separate steps. So first you make another little object. This bit here tells lavaan that you're doing a structural equation model. So you can in lavaan use different operators. So if you're doing confirmatory factor analysis, you'd write CFA there. And then most of the rest of the bit that comes in the brackets would be the same. But again, go and look at the tutorial. There's some really clear examples for CFA in the tutorial. And so these bits here are just, in this case, telling us to use this data set that I've created before. So it's a sample covariance matrix, and here are the sample means with the objects that I've just created just earlier. If you've got actual data, I'll just show you down here. I'll just take away my little hashtag there. This is what the fit line looks like if you've got your own data. You just tell it what your data is there. So you don't need these 2 bits here, and you don't need this bit. Sample number of observations is 203. So one of the reasons that it doesn't always work out perfectly if you're replicating something you find in the literature is if there's missing data in the examples. When you're doing it like this, you're just saying to lavaan that every observation is there for all those 203 participants, and that may not necessarily be true in real life. So that's often why the estimates are up or down a little bit.
Ellie, can I ask a question?
Yeah.
So when you're doing it with your own data, presumably within that data frame called EBLP data,
yeah,
there are variables that are named the same as the names that you've created over there.
Yeah. So you'd actually just have, these would be your variable names in your data set.
Yeah.
So you do have to have the precise variable names that are in the data file.
Yeah.
And that would be this data here. So it's just the same as in other applications where you would extract your data and turn that into, I'm not very good with the language. You do this. Here is data 1. It's read this CSV file. It's this data here. Header equals true is just brings in those variable names. And so that data 1 might be what you then put down here in this line of syntax. I'm just going to change it because it's just an example. So my data equals data 1 that I've just brought in earlier with these variable names. The std.lv means standardized latent variables. So I'm standardizing the latent variables Sometimes you will want to do that and sometimes you won't want to do that. So there are different reasons for why you might be interested in standardized latent variables or unstandardized latent variables. But in the example that I'm showing you, the latent variables are standardized. And so this should give us the same information around about. And so nothing really has happened. So you just need to then also run this second line here, which gives you a summary of your fit statistics that you've just created here. So fit measures equals true. That will give you the fit statistics that are really common to structural equation models. And we'll have a look at what those are. Standardized equals true just gives you standardized coefficients as well as unstandardized coefficients. And then the R-square gives you R-square values, which have a little bit of a different meaning in structural equation models to in just regular regressions. So if you just run that bit of your syntax, I'm in the habit of just Control Enter to run, and you get loads and loads of information from that, just that one last little line because you've told it what to do. So the first thing that you always look at when you're running structural equation models are fit statistics, because if your models don't fit your data, then you can't interpret parameters. And so that is a bit of a departure from regressions where you're just looking at the beta weights of your predictors. So here, if you had an actual data file, it would come and it would tell you how many observations you had in that data file. And then what we look at first are the chi-square statistics. So in structural equation modeling, commonly you look at chi-square statistics and then you look at other fit statistics, which are often based on chi-square, but some are not. So you might look at the RMSEA, you might look at the CFI and TLI, and all of these have got like rules of thumb for where they should fall in order for you to say, okay, my model is an adequate fit to the data that I have here. So this, the first section here this is actually chi-square statistic. This is the degrees of freedom of the model, and then that's the p-value of the chi-square statistic. And so what you're looking at for model fit is that your p-value is non-significant, because if it's a significant p-value, it's like a departure from, the model is too far of a departure from what the data are. So in this case, this is a really good example because the chi-square is a non-significant chi-square. So we've got 8 degrees of freedom and a chi-square of 12.975. I have a visitor. One of my kids has just come to learn about structural equation models in his UDI. I don't know if anyone knows about UDIs. You have to just listen, okay?
Okay.
And then go away. All right,
I just
good.
want to ask you a question.
No, go and ask Dad a question.
Yeah, but he's in the bathroom.
Go away. This is awesome. Okay, and so then what I often look at are chi-square. If you've got a really big sample size, you'll often find that your chi-square statistic is significant, but that's to do with sample size, and small deviations of the model from the data can be significant in large sample sizes. So that's quite well known in structural equation modeling. And one of the reasons why people, a lot cleverer than me, went away and developed different fit statistics, some of which correct for sample size. And so what I often look at are the CFI and the TLI statistics. These are supposed to be above 0.95. So again, this is looking like a pretty good model fit. And then we'll skip over down here to the RMSEA. Ideally, it should be less than 0.06. And so in this case, we've got less than 0.06. And it always gives you a confidence interval around that RMSEA statistic, but it's a 90% confidence interval for some reason that I don't understand. And then you can also look at this SRMR. So these are all to do with the residuals in the model. So you've got the variance that's explained by the structural equation model, and then you've got some residual left over, and that's what the root mean square error of approximation and the standardized root mean square of the residuals are really getting at in some ways. How much variance is left over after this model has been fit to the data? And so the SRMR is around about the same rule of thumb you're looking at, the less than 0.06. Different people kind of give different recommendations, But if you see model fit statistics like what we're seeing for this model, then you can say, well, this is a good model and we're happy with it. And so once we've determined that the model fits the data, then what you can do is come down here and interpret the parameters. And so what it will tell you is, first, here is our latent variable called deep for deep learning. Here are our 3 variables that we use to create that latent factor. And then there's lots of information about them. And similarly with this isolated learning variable, there's 3 different variables that comprise that latent factor, and there's lots of information. So you've got unstandardized estimates here, like factor loadings, and then you've got standardized standardized factor loadings over here. So sometimes it's easier to kind of conceptualize standardized as opposed to unstandardized factor loadings. And then you've got p-values, and then that can sometimes tell you whether some variables are not very good, are kind of a good fit with others. So they're not really contributing a lot of variance to that latent variable. So that example there, that 3rd variable, the loading's pretty low, it's kind of marginally significant contributor to that latent factor. And so in a real life application, that often what you find is once you run the models, then something that you might have seen in your data collection or the wording of a question or something like that, and you think, oh, is that going to work with these other variables? Interestingly, what you often find is that that's what the numbers tell you when you run the models. They tell you that those are not very good questions in your questionnaire or whatever it might be. Often this information isn't reported. So this is kind of like you have that there for some information about your latent variables. If you've got a larger model, what's more often reported are the relationships between all of the variables. So sometimes yes, sometimes no. So in this case, we've only got a really simple model. And so the only relationship between latent variables is this covariance between deep learning and isolated learning. You might notice that in the actual model, we did not tell lavaan to generate that covariance. So that's one of the features that's built into lavaan, that it will actually generate those covariances between exogenous variables in the model. You can tell it not to, but in this case, we've just left it with the defaults and it gives you that covariance between the 2. In this example, I really haven't shown you how to make latent variables predict other latent variables. So I'll show you that further down below. But what we can do is we can have a look and see whether these coefficients match up with the coefficients in the actual published paper. So if I swap over, if you're running through this with me, you can probably look at yours and then look at this PowerPoint presentation. What I'm going to look at and see is whether there's a deep and isolated learning covariance. Well, let's have a look at the standardized one so we know what we're looking for. Correlation is equivalent. So it's pretty similar, and that would be because why? This is pop quiz. Because those 2 variables, those 2 latent variables are standardized. We asked it to standardize latent variables up here. Standardized latent variables equals true. Okay, so I'm just going to go back here. So we're looking for minus 0.25 as a correlation between deep and isolated. And look at that, that's nice. So it works out. And what you can actually do is then look at all of these. I need that little drawing thing. I'll just circle with my mouse. You can look at all of these factor loadings, and then you can go back to the output, and you can see that all those factor loadings are the factor loadings that are generated by that example of that model. And then what you can also do is you can compare the fit statistics that we looked at with the fit statistics that are reported here. So our chi-square was 12 point something and 8 degrees of freedom. Theirs is 11.4, 8 degrees of freedom. And so that bouncing around really is just that if there's missing data somewhere that's not captured by the way that we're doing this, just as an example. The RMSEA is 0.049, and I think that's pretty much what the RMSEA was.
Sally, can I put you on the spot and ask you a not art related question?
Yeah.
So for those of us who have never done, I've never done structural cohesion modeling, and I look at this and go, what does that mean? Can you tell me what this tells us about deep and isolated learning, and how these factors map onto those things, and what we learn from this kind of diagram?
Yeah, well, this example, I mean, I don't really know anything about deep and isolated learning, so it's used just an example. But basically what it tells you is that we can capture this latent concept of deep learning with observed variables. So there's 3 observed variables that are measured. And so you'll have your data file and you'll have, maybe they're measured on a 5-point Likert scale, maybe they're measured with some kind of, in this case, it's like term papers. Can they read critically? Can they compare and contrast? So it doesn't really matter what the scale is of those variables that comprise the latent factors. But like with lots of quantitative statistics, you're really looking for measures that capture variability in those indicators. So I think like the rule of thumb is no less than 5 points on your Likert scale. That seems to work pretty well. Some of the variables I work with have 7 points, but then some educational data, NAPLAN, for example, I work with a lot, and the scale is 1 to 1,000, and it's purposely designed as a ratio scale so that each step up the scale is equivalently spaced. So it's the perfect kind of data to use for these types of models. What you're also doing, and you can see down in the bottom those little E's, and those 0.77, 0.04, that's the error or the residual left over from the observed variable after the shared variance is captured by the latent variable. So you can see there's quite a lot of residual in this term papers one, but there's really not very much residual left over here in this read critically one. So one of the things I think that attracts people to structural equation models is this idea of kind of partitioning out the error in observed variables and making these latent factors that are comprised of several observed variables, but kind of bypassing the problems you get with just doing averages. If you've got several variables and you do an average, you kind of just incorporate all the error in there. But structural equation models are one way of getting around those problems with error in observed variables. Is that like, did that answer your question?
That's super helpful. Yes, that's so good. And the minus 2.25 relation between deep and isolated in this case tells you that those are capturing totally separate things, separate variants.
Well, they're not totally separate. That's like that's basically like a regression coefficient. So the coefficients between the latent variables, and because that's standardized, so you've got a mean of 0 and a standard deviation of 1. So you can sort of think about it in the same kind of magnitudes as correlations in a sense, I guess.
Right.
Although you can go above and below 1 for standardized variables. So there's a negative relationship between deep learning and isolated learning. And so for whatever reason that negative relationship exists between those 2 factors, people who are better at deep learning are not as good at this isolated learning thing. I remember reading this paper. I haven't read it again. I read it last year, and I remember reading it and thinking, oh yeah, that all makes sense. So it's actually quite a really good kind of entry to what's actually going on with these models. So I highly recommend you go and have a look at that paper if you're interested in these models.
Thank you.
I'm not sure what I might do. So we'll run through the next example because it's the same model, but what we're doing is we're kind of almost building in a mediation model into this, into the wider structural equation modeling framework. So what we have here is this course achievement overall variable, and then we're using deep learning and isolated learning to predict course achievement, and then isolated learning. In this case, if you notice the difference here, this is just a correlation between the 2, no directional relationship, just 2 domains that are correlated. Here, the theory is that isolated learning predicts deep learning and that it also predicts course achievement, and that deep learning predicts course achievement as well. And so once the arrows are directional, the idea in structural equation models is that that's now a causal relationship. And so that's where you run into problems sometimes with cross-sectional data. Nonetheless, let's run this example and have a look and see whether we get the same. These are basically the same as regression, standardized regression coefficients. So do we get a regression coefficient of 0.24, deep learning predicting course achievement? And do we get minus 0.22 for isolated learning predicting course achievement? And then up here is an R-square value. That's the amount of variance explained in this observed course achievement variable. So how much variance is explained by these two predictors? And so that's the same concept as what you get in normal regressions. We're just building it into this bigger model. So let me go back, and I will remember to press all buttons this time and run all the sections. I'm just going to get rid of that. Okay. Model 1 in figure 5. And so here's example 2. Oh no, this is CFA model with correlated factors. Here it is, model in figure 6, the mediation model with 2 latent factors predicting achievement. And so you'll see we're using the same data frame that we used before. It's the same variables, but we're bringing in this variable called achievement. And so up here, remember I said that if you've got extra variables in your data frame that you're not using, that it doesn't matter. I actually had one more variable up here, achievement, that we didn't use in this first example. So I'm just going to bring that variable in. So here in model 2, I'm making the same latent factors with the same indicators. And then I'm going to predict deep learning with isolated learning. And so that's this little, I can't remember what it's called. What's this called? Squiggly line.
It's tilde.
It's a tilde. That's what it is.
T-I-L-D-E.
Yeah.
Tilde.
So deep learning is predicted by isolated learning, and achievement is predicted by deep learning and isolated learning. So it's easy to write these models at a very basic level. Just if you know the right operators, and look on the Lavaan website if you can't remember them, if you know the right operators and you identify your variables, then you'll be able to write these models. The tricky thing is to get them to fit and then to interpret the parameters and see what you can do if they don't fit. So there, I'm just going to run my model 2, and then the same fit measures. In this example in the paper, they said they only had 194 participants for this particular section. So run that bit, and then we'll run our summary, and you'll get the same sort of information out as what we were looking at before. So first, just have a quick look at fit statistics. If you're going to go ahead and do structural equation models, I highly recommend that you go away and read up on fit statistics. There's some really good stats textbooks. I've got one particular recommendation, so if people would like it, I will put this. I'll find out the citation at the end and give that to you. But there's lots of papers that kind of puzzle through this issue of, well, what are we actually doing with fit statistics, to try and avoid this kind of scenario where we have a cutoff and that's it, and we're only just working with our cutoff. So there are different fit statistics which are better in different applications. So again, here we have a chi-square value of 18.88 and 12 degrees of freedom, which is non-significant, which is always what we like to see. Although don't panic if you have a big sample and you're always getting significant chi-square, that happens all the time. And then the CFI and the TLI are also looking fairly respectable. They're both above 0.95. Then we have the RMSEA is below 0.06 with a confidence interval that goes from 0 to 0.09, which looks fine. And then the SRMR is also below 0.06. So again, this is saying this is a pretty good model. We can interpret the parameters in this model. So again, we get the same information, deep and isolated learning, predicted by these observed variables, and you'll get very similar loadings on those variables, even though you've brought in another observed variable into the model. One thing I will say is that if you do get bad or poor model fit statistics. One of the things that I see a lot that the problem is will be with the observed variables predicting the latent variables. And so there's ways you can actually test where your model fit, your poor model fit is coming from. And a lot of the time it's coming from not very good observed variables. And so I know people want structural equation models to fix up the issue of bad measurement, but unfortunately it doesn't, because your models won't fit. And so then you can't interpret your parameters. So that's just one thing just to watch out for. There are ways that you can check whether that's where your model misfit is coming from. And so now this time we've got this little heading called regressions, because we've told it which regressions to do here. And so in this case, we've got isolated learning predicting deep learning, and that, I think that was the value we were looking for. It was minus 0.25, same as what it was before. So it hasn't really altered the relationship between those two variables, incorporating this new observed variable. And then deep learning is predicting achievement. Well, over here, if we look at standardized, it'll be 0.24. And isolated learning predicting achievement minus 0.25 if we're rounding up. And if I just flick back to the PowerPoint, let's have a look and see if we get the right. Yeah, so we're getting values in the realm of what's reported here. So that's a negative predictor, that's a positive predictor. And then that's that negative predictor between those two. So if you're familiar with mediation models, this is sort of the first step in a mediation model. You can also, I'll show you, I think I've got a little bit of code down the bottom that will show you how you can get the actual mediated pathway, because you can use lavaan to do that as well. Okie dokie. All right, I just wanted to have a look and see whether the R square comes out similarly. So the R square we were looking at was for the, what's that variable called? Achievement, ACH. And I think in the example, it said 13% of the variance was explained. So here we have 0.14, 14% of the variance in that achievement variable is explained by those two predictors. And so we've got also variance explained in the deep learning variable, because it is actually predicted by something in the model. But we don't have variance explained by the isolated learning because it's exogenous. So it's only predicting other things. And then we've got how much of the variance, these ones are slightly different interpretation. So this is how much of the variance in those observed variables is captured by the latent variable model. So it's a little bit of a different concept, but it's all to do with variance being explained in either observed or latent variables. Okay. So I can see someone in the chat. What's considered a big sample? Okay, sample size in structural equation modeling is a challenging topic. Big samples, yeah, I mean, I don't know that I would believe a model with any less than 200 observations, so 200 participants in your study. But even then, I don't know. Yeah, the smallest sample size I've had in my PhD was about 600. And even then I was a bit like, yeah, is this enough? And it was a longitudinal model, so there were repeated measures, which is an advantage. But yes, I've got quite a good chapter about sample sizes in structural equation models, Bernadette. So you can, I think Bernadette, you can email me if you like. I'll share my chapter with you. It's one of those areas that's hugely, hugely contested. Because people with small sample sizes want to be able to say, oh, I can do structural equation models, hooray. And other people go, no, that's not a big enough sample size. Your estimates won't be stable. You won't be able to replicate what you've done there, and so on and so on. So it's really, yes, sample size planning is challenging at the best of times, but for structural equation models, yeah, and it also depends if you're doing a repeated measures model. It depends also how many indicators you have loading on your latent factors. There are online calculators for sample sizes in structural equation models as well, which you can look up. Just Google sample size calculator structural equation model and something will come up. And you can, but in that case, you have to sort of have a really good kind of grasp of how many indicators are you going to have, how many latent variables, how many regression coefficients are you going to estimate from your data. So you need to have a really clear concept of what you're doing before those sample size calculators will work. Okay, so this is a second example. This one is a much more complicated model, but interestingly, it's only got one latent factor. So EF stands for executive functioning, and it's comprised of verbal working memory, spatial working memory, inhibition, and planning. So there's 4 observed variables that load onto this executive functioning domain, and then all of the other variables are observed. So in the kind of tradition of visualization of structural equation models, the oval shapes are always latent variables, the square shapes are always observed. And then little round circles are for error, but people don't always include those error terms. As you can see here, there's no error terms included in this model. What I like about this example is that the variables have a temporal order. So SES was measured first, executive functioning and verbal fluency were measured next, and then reading and maths were measured later. And so the idea is that because you've got this temporal order, it helps with your causal inference. So the things that precede reading and math are in some senses causing them. They're not just co-varying with them, which is a different kind of concept. And so in terms of education research, thinking about where and when interventions should be put in place, that temporal order of things is really important. And I don't always very often see structural equation models with this temporal order built in, because people tend to then move to, if they've got repeated measures, they tend to move to latent growth curves or some kind of growth modeling instead. So this little chart here in this PowerPoint, this is just taken from the paper as well, and it's just what the factor loadings are for those observed variables on executive functioning. So if we go back, I'll just go back to that, we'll have a look. It looks complicated, but you can actually just read it and translate it to the code. It's kind of like those, we were talking at dinner this evening with my kids about verbal maths problems, where you have to, you know, your train's going at 100 k's an hour and the wind's going this way and whatnot. So it's kind of like that, but yes. I'm just going to run all of this together so don't skip out any bits this time. And that's going to create, so name the variables. The means and standard deviations in this case are not standardized. So we have observed means, unstandardized, and then what the standard deviations are for those variables. And so you can just put those in. And then this was my the CSV file, which was just the correlation matrix with ones on the diagonal. And then you have to put the correlations on both diagonals for this to work. Okay, so the first thing I'm going to do is just see if I can run this latent variable model with these 4 indicators of executive functioning. So that's what this model here is. Executive functioning is comprised of verbal working memory, spatial working memory, planning, and inhibition. And then we'll just go flick back to the PowerPoint and see whether we get the same loadings. And so again, you'll notice here that even though I've used SEM, this would work the same if I had CFA written there, because this is just a confirmatory factor model, basically. But I'm not going to change it because it might not work. I'm just going to keep it like this. All right, let's have a look at our summary. Okay, so even for a little confirmatory factor model like that, it's just one factor. I'm seeing whether these items load on this factor. We'll get some nice fit statistics out of this. And so here I am, there's 2 degrees of freedom, and the chi-square is 2, so that's fine, that's non-significant. There were 203 observations in this data set. And then we can have a look at the other ones. The CFI and the TLI also are fine. Both, this one's above 0.95, this one's a little below, But what I think the best practice recommendations are, you collect up lots of information about model fit. So you don't like fall into decline because one of your model fit statistics falls below the cutoff that someone wrote about in 1985. There's your RMSEA, which is below 0.06. And then there's your SRMR. Of course, I'm looking at you laughing, Jenny. If if all your model fit statistics are bad, sure, you can try to argue that it's fine and you can interpret your parameters, but you will get someone coming along and going, no, you can't, no. This one as well, look at the confidence interval around that RMSEA. So it goes up to 0.15. I suspect in this case, that's got to do with sample size. So there's just not enough observations to really, like, it's interesting how I think about this. I think about this from my English teacher, interpretive brain. It's not enough information to make sure that this model is actually a really good fit to the data. Because you've got a lower number of observations, the confidence interval is wider. So it's what's the, like, how confident are we that this data is fitting this model? And in this case, yeah, it's okay, it's looking fine. But if lots of these model fit statistics are looking really poor, then you have to take a step back and go, well, what's driving this misfit? So what's going on in my model that's making it not work? In this case, what I did not do in this line of code is, and I wrote it down here so that I would remember, I didn't put in standardized latent variables equals true. I left that out because we wanted to see what happens when we set the first factor loading at 1. So in factor analysis or confirmatory factor models, you've got to scale your latent variables somehow. And so often it's built into programs where the first observed variable will be the variable against which everything is scaled, or you can tell it to standardize everything. And in that case, the latent variable is standardized with a mean of 0 and standard deviation of 1. But you can sort of look at what happens in both cases here, because these are unstandardized loadings, and then the standardized loadings are over here anyway. So you can sort of see what's the strength of the loading of each of these variables on that executive functioning factor. And you can see here that this inhibition one isn't particularly good. And these are not, remember, these are like, these standardized ones are between 0 and 1. So they're not super high loadings. They're okay, but they're not, for something which is a latent factor that's supposed to be capturing this domain with all these observed variables, you can get better results than this with different observed variables. So it's always a bit of a balancing act between variables that are capturing different facets of a latent construct, and then variables that are fitting together well enough to be a latent domain. That's kind of like there's not a set way that you evaluate that. It just comes from experience and looking at all these examples. Does someone have a question?
Yeah, Sally, it's John.
Hi.
Hi, thanks for your presentation so far. There's a couple of statistics down. Does it look like the standard deviations are negative? What's happening there?
Which, yeah, in this intercepts bit?
Yeah.
Yeah, so you can have negative intercepts. Can you not?
It's the standard error on the intercept, isn't it? STD, LV and STD all.
Standardized latent variable.
Oh.
Yeah, and that's when everything's standardized. So observed and latent variable.
I misinterpreted it.
Yeah, no, that's fine. It will tell you if you have negative variances, and like it'll throw you up a big warning about Hayward cases. And I have no advice for those for those instances, because that's really challenging as well. Like, what do you do when you get and there's all sorts of reasons that happens, and I'm not a good enough expert to know what to do in those cases. I wish I knew a good enough expert to tell me what to do when that happened, Anyway, I don't. Yeah, so the final bit you get is just the R squared, how much of the variance in those observed variables is being captured by that latent factor. So the reason I show you this is because here is an example. I remember when I looked at this example, it's an example of where if you get model misfit in a larger model, I would suspect it would be driven by the latent variable, like what's called the measurement part of the model rather than the structural part. So the measurement part of the model is the part where you're loading your observed variables onto a latent variable. And if you've got lots of those, you might have model misfit in more than one part of the measurement part of your model, but the structural part of the model could be okay. But then that, like, matching those two things up together is challenging then, because if your latent variables aren't being measured very well, how can you then interpret your coefficients between your latent variables? And so it's just an example of where we'll run the next part of the model and we'll have a look at the model fit statistics. I can't remember what they are, but if they're not brilliant, it's an example of where it could be driven by misfit in the measurement part of the model. So I'm going to skip over that little bit of information there. So this model is that big model that I showed you a few minutes ago. So basically we are coding in one latent variable, executive functioning, with all of these observed indicators. And then these are all the regressions that we're doing here. In this case, what I've done is I've taken parents' level of education out of the data set as my SES variable. So we don't get exactly the same coefficients because they did some crazy thing with all sorts of other variables to create SES, and there wasn't enough information in the paper to pull out that information. So I've gone with parent education as a proxy. So parent education predicts executive functioning, parent education predicts verbal fluency, and then reading is predicted by parents' education, executive functioning, and verbal fluency. And so that's this executive function is created up here, coded in up there. And then maths is predicted by those same three variables. And then there's a covariance between executive functioning and verbal fluency. In this case, I know in a previous version, Lavaan's defaults let it build in a covariance between exogenous variables. But in this case, because these are both being predicted by something, you've got to tell Lavaan to put that covariance in. So 2 tildes in a row is a covariance. And finally, there's a covariance between reading and maths. So there's lots and lots of paths in this model. So if you run that bit, and then we're going to run our fit section and make that object. And then we're going to do the summary. We go up to the top. Again, we'll have a look at model fit statistics. And they're actually looking fine. So there we have chi-square, degrees of freedom, and then it's non-significant p-value. Now I have 2 children. Hi, kids.
Hi, it's checking the time.
It's time to go to bed.
Yeah.
I think one of my kids is like, he's lying on the floor just absorbing about structural equation models. Great.
I'm good.
He's
You can
fine.
never start too young, right? To just like by osmosis
That's right.
learn about Lavaan.
He's just absorbing the information.
I was checking.
Okay, shush, you have to be quiet.
I'm not-
Here we have the CFI and TLI. I mean, technically they're bounded at 1, but they can give you back estimates over 1, and they're just telling you that that's above 0.95, so your model is fitting really well. And then the RMSEA, again, it's basically 0, and the SRMR. So there's not a lot of residual left over that's not being explained by this model. So you've got a really good fitting model in this case. So we've had a look already at that executive functioning latent variable. Let's have a look at the regressions. I can't remember whether they're reported as standardized in that diagram or not standardized. I think they're standardized, but we can see here they are. So there's positive relationship between executive functioning and our SES proxy. There's a positive relationship between SES and verbal fluency. And then there's reading is predicted by our SES proxy, executive functioning, and verbal fluency. But look at that, that's a non-significant predictor because here's the p-value here. And then here is another non-significant predictor down here. Verbal fluency doesn't predict, well, the relationship between verbal fluency and maths is not significantly different to 0. And so if we go over to the PowerPoint, you can see that's exactly what we've got. Verbal fluency does not predict reading and it does not predict maths. And so you can work your way through all of these coefficients. And even though I'm using parent education as a proxy for SES, these predictors are very similar as what we see in this diagram out of the paper itself. So we've got a reasonably strong covariance between reading and maths, which makes sense. And then there's a covariance between executive functioning and verbal fluency. One thing I will say about this model, in terms of the structural portion of the model, so that's this bit down here, not including this, every single path is estimated. So there's a link between every single variable or latent factor and every other one. So it's actually not really a very, like it's, what do they say? I listened to that podcast Quantitude, and it's been very good, like stats learning during my PhD. And they would say something like, this model is not a very brave model. Like you're not being very brave here in like testing out relationships between constructs, because you're actually just estimating everything. So any of the model misfit is coming from the fact that these observed variables up here are just not predicting anything else in the model. So it's an interesting example. You've got good model fit statistics, but the structural portion of the model is what's called saturated. And in terms of how you interpret model fit statistics, what you're usually doing is comparing a saturated model with the model that you've coded in yourself. And so the idea is that you don't have every possible pathway estimated. So it's an interesting, yeah, I just found it to be quite an interesting example that yes, we get really good information out of this model. The model fit statistics are good. These observed variables, some of them aren't the best predictors of executive functioning, but it works okay, like it works quite well. But yeah, it's a good example just to show that, yeah, you can fit a structural equation model, but if you're estimating every path, one, you run out of degrees of freedom eventually. And two, you're not really, it's not a super strong test of any particular theory. So you don't need, if you didn't have those paths between SES and reading and SES and maths, you could look at mediated pathways from SES through executive functioning, for example, to reading. But because SES predicts reading, there's kind of no point doing it because all those pathways are coded in. What's the difference between standardized LV and standardized all? Let me just flick back and I'll tell you. What's the difference? Standardized latent variables is where just the latent variables are standardized. So in this case, we've only got one latent variable, and that's executive functioning. But standardized all is where every variable is standardized. And it's really up to people's preference, what they interpret and report. In education research, there is a big push to talking about effect sizes. And so because effect sizes are standardized effects, essentially, they're sort of easier for people in the education literature, and particularly if you're trying to communicate things outside of academic journals, reporting standardized effects seems to me to be easier for people to grasp than like some things standardized or unstandardized coefficients. Yeah, people probably have really strong opinions on this, but I like standardized variables because even if a pathway is significant, quote unquote, the effect can still be small. And so then what do you do with that? Is it to do with sample size? Is it to do with, I don't know, any other reason? So it's a good way to kind of think through what are the implications of finding a significant effect, but the standardized effect is only 0.10. Like what do we make of that? Is that is that a useful effect? Do we know what that means? So that kind of gets into a different issue, but yes, that's what the difference is between those two, standardized latent variables and standardized all. Oh, okay, this is where the mediation bit is. So in the paper, there is an example of an indirect effect. Oh, let me just check the chat. Okay, thank you. Good, I'm glad my explanation was good. Sometimes I just ramble on. You can run mediation models using lavaan, which is probably one of the attractions for people doing psych honours degrees. Everybody likes running mediation models. So you can actually do that. It takes a little bit more complicated kind of telling the program what to do, but it makes you think through what your total direct and indirect effects are and how they're actually created. And so here I've just done this example of, well, how do you get the mediated effect from, let's say, the direct effect. I can't even remember what the mediated effect is. Executive functioning, A times parent education, reading. Oh, so they must have reported an indirect effect from SES through to reading, even though all those paths were already estimated. And so that's what this is. This is the mediator here. The part of the model which is telling it what variable is the mediated variable. So it's a bit confusing. And again, this is in the lavaan documentation. If you want to run mediation models, let me just run it and I'll show you what extra information you get out at the end, because it will tell you what the mediator is. Quite nice what it tells you. It goes, so it's the same model, you've just added in a mediating pathway. And look what it gives you down here, define parameters. There's your A times B path with an estimate, and there's your total effect. So it's the total effect and the indirect effect that it's reporting here. And then it tells you whether they're significantly different from 0. And then it gives you unstandardized coefficients and then standardized coefficients. So that's kind of nifty. And I'd have to go back to the paper to see whether this replicates what it says in the paper. From memory, I'm pretty sure it's pretty similar. So yes, again, if you want to run mediation models, it's worth going into the lavaan documentation and working through that, because this is how I figured this out. I went through and I just matched what the documentation said with what I wanted to do and then ran it. And then it brought up this nice little explanation down here. So that was quite a good, I think I learned that because I've not ever done a mediation model. I just learned that for this example because I thought it would be cool. So obviously you can get bootstrap standard errors, but it doesn't work with a variance, covariance matrix or correlation matrix. And that's for obvious reasons, I say, because you don't have the data to resample from. So that's just in there just so that you know that you can get bootstrap standard errors and report those if you've got an actual data set. So what's the time? 8:15. Would people rather meet, will I have time to talk about modification indices and latent growth curves, do you think?
You have as much time as you like.
Okay, because it's 8:15. Yeah, okay, I probably will.
If people get sleepy, then they'll just drop off and go to bed.
Okay.
I'm keen for both.
Okay, cool. All right,
Yeah.
well.
And the recording is there. So if people do get sleepy and drop off and go to bed, it'll be on Our Ladies Global YouTube sometime tomorrow if you want to catch them.
Yeah. Okay, cool. So one of the things that you will come up against if you do go down the path of doing structural equation models is something called modification indices. So if you get poor model fit, you can ask whatever package you're using to give you modification indices, and they will give you some kind of indication of how much better your chi-square statistic will be if you build in other pathways in your model. And so this can be anything. So it can be residual covariances between variables loading on the same latent factor. It can be different regression coefficient pathways in the structural portion of the model. It can be like cross loadings between variables that are supposed to be loading on one latent factor, but the model is telling you that variable really wants to load on another variable too. It can be anything like that. And now it is like a bit of a rabbit warren you can go down the modification and indices pathway and never come out, because what you're pursuing then is like ever more better model fit. But the danger is that once you start building in modification indices, you're no longer testing a theory. So that's one of those things with structural equation models. What you're supposed to be doing is having a theory, making a model and getting some data and testing that theory. But once you look at modification indices and change your model according to modification indices, it more is just like data exploration. So you're just kind of looking what's going to happen if you build in a modification index and so on. So I'm going to give you an example of what happens if you have a model and then you choose to use a modification index to get a better model fit. As compared to the model that's actually reported in the literature. So this is the same example we've been working with from the Albert 2020 paper. So the first thing I've done is I've changed the model. So what I've done is I haven't used parent education as a predictor of reading and maths. I've just dropped that out as a predictor completely. And so I've got this different model here. And I haven't got in my covariances either. So remember how I said that the model with the saturated structural portion of the model isn't very like brave model. In this case, what I've done is I've dropped out some of those pathways. So I'm going to test what happens when I do that, have a look at the model fit, and then see what the modification indices would tell me to do, just as a kind of like a cautionary tale. All right, so there's that model. Here is our fit, and then we go here and look at the summary. Okay, so let's have a look. Remember, our model fit statistics before have all been really good. And in this case, the chi-square is 75 and the degrees of freedom is 17. So that's not telling us that this is a particularly good model. And then if we look at the CFI and the TLI, these are both like well below 0.90. So this is an example of where you go, oh, my model's not that good. My model and my data don't go together, essentially. The RMSEA is way too high. The SRMR, I mean, you could almost argue that's passable, but one out of all of these other fit statistics, you probably won't convince anyone. So rather than interpreting parameters, I'm going to do what you probably should do, and that's not interpret parameters because the model doesn't fit the data. But what I'm going to do instead is have a look at modification indices. So if I just run this bit of code, so I'm using this object here, this fit, I'm going to use a minimum value of 10. So it's going to give me back every modification I could make to my model, which would improve it by at least 10 chi-square increments. I'm not quite sure what you call them. And so then it gives us some information down the bottom here. This is all the modifications I could make. This column here, MI, they are the chi-square increments you would improve by. And that's really all you need to look at in this case. So what it's telling me is if I put a covariant, if I put a regression coefficient in between reading and parent education, interesting, because that's what the model originally was. And then it's saying there should be a covariance between verbal fluency and reading. See, that's giving me 27 chi-square increments of improvement. Verbal working memory and verbal fluency, that's an interesting one because verbal working memory is one of the observed variables that loaded onto executive functioning. So here we're having another variable wanting to have a covariance with two observed variables wanting to have a covariance, but one of them is actually supposed to be loading on a latent variable. And so it starts to get a bit confusing about what these actually mean if you build them in. And so then what I decided to do was go, oh, okay, all right, well, I'm going to build in, I don't know why I decided to do this. Maybe I thought, well, build in executive functioning covarying with verbal fluency. And those were the two that were there before. So I'm going to put those two in, but I still don't have parent education in this model, predicting reading and maths. So I've left in now these covariances between these two. fit 4 and fit 5. Oh, before I do that, let's have a look at fit 4, model 4 was our model up here. This model, which was from the paper. And so what I'm going to do is I'm just going to show you this little piece of code, which allows you to compare what's called nested models. I always found that terminology confusing, but it's models that can be compared because they've got the same parameters estimated, but one model will have fewer. So it's essentially the same model, but we've left out some of these other parameters. And so what it gives you basically is a difference in chi-square. So the model that's reported in the literature, the chi-square is 11.56. And this model that leaves out that parent education predicting reading and maths has got a chi-square of 75.43. If you're doing model testing and you're comparing different hypothesized models, you might be interested in this comparison of chi-square statistics to tell you which model is a better fit to your data. I do that quite a lot in latent growth models, attempting to demonstrate which model is the best fit to a longitudinal trajectory. And I'll show you that at the very end. So imagine I use the modification indices from model 5, which were these ones here, and add some paths in my model. So what I've done is I've added parent education as a predictor of reading, which was this first one. Sorry, I didn't read down before, I read up instead. And that was one of the highest modification indices. And then I added a covariance between executive functioning and verbal fluency, because I thought that these other ones, I should have added it between reading and verbal fluency, never mind. I thought that these other ones didn't make sense. For whatever reason, I thought they didn't make sense at the time. And so that's the danger of modification indices. You can just go, oh yeah, I'm just going to add these modifications, it'll be right. And so I've added those into my model. I've added parent education here, and I've added this covariance in there. And then if I run model 6, and then what we'll do is we will get some fit statistics out. And then again, I'm going to, rather than read the fit statistics up here, first I'm just going to check what the difference is between them. And so remember, model 5 was 75.43, and model 6, the chi-square has reduced significantly. And so in these cases, you're looking for chi-square that reduces by a significant amount. So compared to the number of degrees of freedom difference. And so in this case, you can say, oh, well, this is a significant improvement in model fit, and therefore model 6 is better. However, then you also run into these problems of, well, am I testing a theory anymore if I do this? And if I could go up here, I can have a look at my other fit statistics. This model looks fine. So this is, you know, it's a significant p-value, but it's not terrible. Not one of the rules of thumb that people say don't use it, but everybody does, is your chi-square around about twice your degrees of freedom or less, around about. And so that's looking kind of all right. These look sort of marginal. These are passable. The RMSEA is looking passable. The SRMI is looking fine. So, okay, good. I've got a model that fits now. I can interpret my parameters. But compared to the theorized pattern of relationships between variables in the PowerPoint, in here, we actually don't have some of these paths that are in their final published model. So you've got to be really careful with the modification indices. And if you want a really like a nice introduction to where it can all go wrong, again, I totally recommend listening to Quantitude, and they've got an episode called something like Modification Indices Whack-a-Mole or something. And it just, they do go through quite clearly that every modification index that you add into your model, it kind of resets the whole thing. So it's not like you can add all the modification indices in and it will have this, each one will have the same effect. They all actually create different chi-square statistics. So it's not as straightforward as going, I'm just going to pick this one and pick that one and pick that one, and my model's going to be fine. And not to mention, you've really moved away from that theory testing framework. Oh, thanks, Jenny. There it is. I think what they've got on their website now, like different topic areas. So some of the podcasts grouped under topic headings. So they might have a structural equation modeling topic area that you can have a look at. Okie dokie, so I will actually have time. So I guess the takeaway point is beware of modification indices. I've been having a fun time using them to kind of demonstrate in confirmatory factor analyses that items which are supposed to create composites are not always very good items. They don't always work very well. So if you've got 20 items and they're supposed to load on 4 factors with 5 items on each of the factor, and then you look at the modification indices and you've got huge cross loadings, like you get poor model fit, and then you get huge cross loadings between items which are supposed to be on one factor and want to load on another factor. It's just another piece of evidence that those observed variables are not really capturing the things that the scale documentation says they should be capturing. So it's just another way that you can, it's kind of like looking in the background of what's going on with all these numbers. So the last example I'll give you, I'm just going to give you a really brief example of how you code in a latent growth curve. So this covariance and mean standard deviation table is just out of the paper that Jenny saw of mine on the conversation. In that paper, I did look at group comparisons, but we can't really do that just with the correlation matrices. So what we're going to do is just fit a latent growth curve model and then use model fit statistics or chi-square comparisons, chi-square 2 degrees of freedom comparisons, to have a look at whether linear growth or non-linear growth fits these data better. So you can see just from this information that the mean scores do increase. I think the example I've got is reading. So the mean scores for reading go up, and this is NAPLAN data. So these mean scores are very close to the national averages if you drop out the states that perform the worst. So if you just take the average to high performing states, this sample that we have is pretty average. And the sample didn't have any children from those states that get consistently the lowest NAPLAN anyway. So it does reflect to an extent the population, even though we've only got reasonably small samples. It's only a sample of 1,119 at the largest. And there's some missing data, but that is not an insurmountable problem if you've got repeated measures. So you can use every piece of data that you have for every individual in your sample, even if they have missingness on any one occasion. So in NAPLAN, you often find there's missingness, say a kid would just have been sick in year 5 and they just didn't show up to do the NAPLAN test. Or maybe they, I don't know, I've been a teacher, they missed the train. Oh, miss, I missed the train and I couldn't do my NAPLAN test. Oh no. So in those cases, it doesn't matter. You don't have to have complete data. In this example too, the way that the study was set up meant that I think 2 cohorts of students are yet to do year 9. So we don't have their data, which is why this number is lower, but that's missing by design. That's not missing, missing not at random, which is what you don't want. Anyway, so you can see the mean scores go up. If you map those mean scores, you can see this kind of curved line. It doesn't go up in a nice straight line. And that gives you a little bit of an indication of what's going to happen with comparing a linear versus a non-linear model. And then you get these correlations between time points. This is what you see all the time in NAPLAN data. The correlations are really high. So the rank order stability of individuals in the sample is pretty stable over time. But that doesn't tell us a lot about how growth unfolds. And so that's what the growth curve modeling is about. Okay, I'm just going to get rid of that. So here's an example of latent growth curve model with 4 repeated measures. One of the advantages of having more than 3 repeated measures is that you can test the functional form of the slope. So you have to have at least 3 repeated measures to fit latent growth curves. But if you've got 3 repeated measures, you can only fit a linear model. And so if your growth is non-linear, then your model may not fit very well. So it's like somebody designed NAPLAN so that you could run latent growth curve models. And I've been surprised to note that not very many people are doing it. I think more people should, because there's loads of interesting research questions we can answer about achievement and developmental patterns of reading growth and so on and so forth with NAPLAN data. So what I've done is I've just imported the mean scores and the standard deviations from my correlation matrix from the paper. And then I've done the same as before. I had the correlation matrix in a CSV file and I've just brought that in. Okay, so the first step in latent growth curve modeling is to fit a linear model. And this is where you expect that the increment of growth between every time point is around about the same. So the average increase in NAPLAN is around about the same increase over time. Now, you don't have to have increasing curves in latent growth curve modeling. You don't even have to have like a slope. You can actually fit a model where, which goes basically flat over time, and that will still work. But you'll just find that there's no growth. So you might find that there's variability in the intercept and in the intercept, but maybe there's no variability in the slope. There could be variability in the slope, even if it's going flat across time. And you can find that there's a negative slope. So maybe, I don't know, there's lots of examples. Maybe people in psychology, if you have an intervention that's supposed to improve somebody's functioning, and that scale is the higher the score, the worse your functioning. If that improves, then the scores will go down, and then that will be a negative slope. So the slope doesn't have to go in any particular direction. Just in achievement data, because of the nature of achievement data, it usually goes up, and children improve as they age anyway. And so that's the kind of expectation you would have. So latent growth curve models, writing the model is a bit different to what we've looked at previously tonight. In this case, we're creating an intercept latent factor and a slope latent factor. And we've only got 4 repeated measures. For the intercept, you force each of the repeated measures to load at 1 on that intercept factor. And what that will then do is it will give you a mean for the intercept and some variance at the intercept. And that mean represents the average achievement at the first time point. And then you have a slope factor. And then these numbers here represent the shape of that slope. So in this case, when I'm forcing it to be a linear model, each measure goes up by 1 increment. 0, 1, 2, 3. So you're starting at 0. 0 is like your intercept. And then you go up by 1 increment to the first year, 1 increment to year 7, 1 increment to year 9. So you can use any number. You could go 0, 2, 4, 6. Your model fit will be the same, just your parameters will be slightly different because you're saying, oh, okay, it's 2 years of growth. So it's 2 there, it's 2 there, it's 2 there. So if we run that, so I've said note the slope loadings because that's how you test the shape of your trajectory. And then, so we run that and it's the same as previously. We just test a growth model. We fit the growth model. In this case, I've actually, I don't really need to have this in here. Standardized latent variables I've made false. I don't want standardized latent variables because if I have standardized latent variables, then I can't interpret the mean and the variance at the intercept and the mean and the variance of the slope. And here I've just kind of gone for a middling estimate of 1,000 observations because, as I said before, there was some missingness. And so in this case, it won't be an exact replication of what's in the paper. But it actually, I only did this last week. I was surprised that this worked. I was like, yes, it works. It's cool. And so here is our fit statistics. There we go. I have to think about it for a second. It gives you out the same sort of information, but in latent growth curve models, the interpretation is a little bit different. So the first thing I'm looking at before we interpret are my model fit statistics. And look at that. That's not very good. It's showing reasonably poor fit to the data. So in latent growth curve models, one of the reasons you have poor model fit can be because your hypothesized trajectory is not the trajectory in the population. So you can test different trajectories and compare models. And so then we have a look, no, those model fit statistics aren't very good. And the RMSEA is particularly bad. SRMR is kind of all right, but I think the recommendation for structural equation models is to interpret RMSEA before you'd interpret SRMR. So before we have a look at the information down here, because it's not very good model fit, so we can't really interpret it. Well, what I might do is just show you this section. Because we have forced our latent variables, we've fixed our latent variables, the intercept on the latent variables to be a number, we don't get any standard errors or p-values or anything like that. And then here is where it shows you on the reading slope, these are the increments of growth. So I've forced year 3 to be 0, year 5 to be 1, and so on and so on. But let's not interpret it because it doesn't make any sense to interpret. Let's go to the next part. I've just shown you what you do when you have a full data set. You just don't need those middle bits, these bits about telling the data, what the data set is. Okay, so the second example I'm going to show you is something called a latent basis growth model. And what a latent basis model does is it sets the increment of change at 1 from your first time point to your last time point. And then it lets the model estimate how much change then is between the first time point and the second time point, how much change is between the second and third time point, and how much change is between the third and last time point, and so on and so on. And so if you've got a really interesting nonlinear growth pattern, then these values can go up and down. In this case, because it's NAPLAN data, I'm expecting them each one to go up, but they'll go up by different increments, which is why a linear model didn't work. So there's my latent basis model. You see here, year 5 used to have 1 star year 5, forcing year 5 to be 1, and year 7 used to have 2 star year 7. Here I've just put them in. So it's going to allow the model to estimate the loading. And then here is the 1. So you can do it, you can also do it in the way where you go, I'm going to make the increment of change. What you're doing is you're just setting an increment of change and you're letting the other increments be relative to that increment. I quite like setting it at 0 at the first time point and 1 at the last time point for NAPLAN, because then the information you get from the model tells you on average how much progress kids make from year 3 to year 9. And I'll show you how that works. It's kind of a fun feature of data that's so well known. If you've got repeated measures that are not in such a well-known framework, it can be a bit more tricky to fit a model. Okay, let's run that. Let's just look at model fit statistics first. Ah, look at that. So that's heaps better. And what I can do too, I'm going to be scrolling up and down a bit. Remember my comparing this model with that model. If I run that, then it will give me the difference in chi-square at relative to degrees of freedom between the model which forced the increment of change to be linear, so the same increment each time, with this curve trajectory. And that's a spectacular improvement. So 2 degrees of freedom difference and 276 chi-square values, whatever they are, better. So it's a heaps better model. So I'm looking at this and I'm going, I'm happy with this model. So there's the CFI and TLI are both 1. The RMSEA is really good. So we can report this and we can say, this model is a good fit to these data. And so we've discovered something about the functional form of growth on average amongst these students over time. So in this case, remember before we just had 1s for the intercept and then we had 0, 1, 2 and 3. This time we've got a 0 here and a 1 here, and then we've got some other numbers here. Basically what that means is that, so imagine 0 and 1 as it's kind of like 100% of growth. So from year 3 to year 5, kids are making nearly 48% of the total growth up to year 5. And then they make 75% of the growth from year 3 to year 7. So you can work out the difference between that. It's about 28% of the growth from year 5 to year 7, and then the remaining 22, whatever it is, % up to year 9. The interesting thing for me is that these models also fit in population data. So you can request data sets from state governments, and they will give you every kid that's done that plan in a cohort. And you run these models and this is exactly what you see. And the models fit really nicely. Sometimes, occasionally, a quadratic term can be included to represent the rate of deceleration in change, but only sometimes. And so there's sort of more work to be done there to kind of really understand, well, what's going on in those cases where it's always numeracy data? Why does a quadratic term work for that data, but not for reading? And it's to do with the shape of the trajectories and the amount of growth that's made over time. Okay, so let me just go down here and have a little bit more look at the information we get. The other pieces of information, I'll come back to covariances. The intercepts here. So when you're looking at a latent growth curve model, here again, we've got an intercept and a slope, and they are latent factors. So a latent intercept factor, this value here is the mean of the intercept. And that value there is the same value within a few points of the average at grade 3. So what you'll find, in fact, I coded them in up here, didn't I? The value in my data set of the average score at grade 3 is pretty much the same as that value there. Okay, and then the slope has got an average value too. So that represents, on average, how much progress a student's making from year 3 to year 9. And if you subtract 447 from 614, you'll get that value. And so that's not quite intuitive. It's one of the reasons I like doing this 0 at grade 3 and 1 at grade 9, because it will give you these parameters and then they can be mapped on to something that seems really logical. So that's the average rate of change over time for kids in this particular sample. Now, I guess it's interesting, but it's not really giving us more information than what you can get by just looking at means. What I like to look at also then are down here in variances. The reading intercept also has a variance. And so that's the variance it represents the variance in scores at year 3. So how much variability? We might have an average, but there's heaps of variability in that plan at year 3. And then we've got variability around the slope as well. So kids on average are making this amount of progress, but there's also heaps of variability around that as well. Some are making less progress, some are making more, some go up a bit and then back a bit and then up a bit more. So averages tell us one thing, but those variances then tell us some more information that I find really interesting. I know not everyone does, but I do. And then what you get then are variances of the observed variables. And so in that year 3 variable, there's this amount of variance. And then in year 5 reading, there's a little bit less. And then in year 7, there's a bit less. And in year 9, there's a bit less. Sometimes a decline in variances over time is more systematic. And I think when you get that more systematic decline in variances, that's when that quadratic term tends to fit in a model better. But I'm not quite across what's going on with that just yet. And it's like that zone of proximal development. It's the next thing I've got to learn. But the other thing that I find really interesting about these declining variances is when you go back up here and look at this covariance term. So you'll get a covariance. Remember earlier tonight, I said in lavaan, it's a default to output a covariance between exogenous variables. And that's what this has done. I've got two latent variables. Here is a covariance between them. Now the unstandardized one is not very interpretable. The standardized one is just like a correlation coefficient. And so that negative correlation coefficient between the intercept and the slope says that on average, there's kind of a convergence going on across your whole sample. There's heaps of variability at year 3. And then as kids are progressing over time, the differences between the high achievers and the low achievers actually gets a little bit less. And then it gets a bit less in year 7 and a bit less in year 9. And so if you know anything about education research, there's something called the Matthew effect, which theorizes that kids that start ahead make more progress over time because they're building on their stronger skills, their broader knowledge base, their better reading, and so on and so on. The interesting thing about NAPLAN data is that it does not show a Matthew effect. So if you get a negative covariance between an intercept and slope, it's called a compensatory growth pattern, and it's not a Matthew effect. It could be to do with lots of things. It could be to do with the shape of the slope. It could be to do with sort of ceiling effects in NAPLAN data, but I'm not sure whether that's the case because it's a scale of 0 to 1,000. Not many kids are getting up to the top of that scale. So, but on the face of it, it looks like there aren't Matthew effects in NAPLAN, that the kids that are really struggling in year 3 actually are making more progress over time. So they're really being helped to improve in their reading skills up to year 9. That's not to say that everyone's doing brilliantly in year 9. There's still kids that underperform. Maybe the tests don't assess the high achievers very precisely, and that's one of the things that the NAPLAN test developers are working on at the moment. So there's lots and lots of theorizing around why this might be happening. But it's really interesting to see that, and I see it in every single NAPLAN data set that I've looked at, always see negative covariance. The other thing that I like about these models are these R-squared. So this is the observed variables for year 3, year 5, year 7, and 9. How much of the variance in those observed variables is being captured by these latent growth models? And this is really good. So between 76, 73 and 80% of the variance in the observed variables is captured by this growth model. And I think that's really cool because it's sort of saying this is a growth model that is adequately capturing the patterns of growth over time in this particular sample. Let me see if I've got anything else to say. I'm not sure that I coded in how to do a quadratic model. That's just my alternate specification where you have the 0 and the 1 in the first 2 steps. That's all. I didn't write in my quadratic model. Let me just type in how you would, let me go back here to the linear model. If you want to introduce a quadratic term into your model, all you have to do is create another latent factor. And then in this case, a quadratic term, oops, daisies, a quadratic term has got a particular function. Oh, equals, okay. And so what you do with a quadratic term is you just square the value of the linear trajectory and you put that in. Now there's reasons that you do this, and I highly recommend doing some courses on structural equation models if you want to, on latent growth models specifically, if you'd like to do this, because a lot of this stuff becomes clear once someone's explained it better than I have. So that's basically what you do. And then I can run this model and we can have a look. They won't fit very well. I need that to be 3 squared is 9, year 9 reading. And then all you will get is another factor. So if I just run that again, just check that everything's right. Yeah. And I'm just going to run that again. And I'm going to run this again. Oh, there we go. It's saying that, and this often happens, that using a quadratic term is not going to work. So we have a non-positive definite covariance matrix. And that's, yes, you can have it, you can inspect the fit to investigate what's going on. But this happens so frequently that I've concluded that quadratic including a quadratic term is not reliable enough. And so I can still output this information and we can see what's going on. Look at that. We got a negative intercept on our quadratic term. I'm looking for negative variances somewhere. Reading slope, no, that makes sense. Reading that makes sense too. So it's potentially that intercept is negative and that doesn't make sense. So you can force the intercept of the quadratic term to be 0, but once you start doing that, it doesn't make sense. Like, why do you need a quadratic term if you're forcing parameters to be 0? And so I know there are some structural equation model people that don't like latent basis models because they think that it's letting the data drive the model too much because you're allowing it to estimate those increments of growth. But yes, sometimes latent growth models just don't work with the data that you have. They're not linear. You get negative variances on quadratic terms. Sometimes what happens is I find negative variances on year 9 when I try and include a quadratic term. Why? I don't know why. I can't figure it out. But that's how you can do it. So that's how you introduce that quadratic term. And then for me, it becomes really complex interpreting the covariances between the slope and the quadratic term. So once you introduce a quadratic parameter, the slope is the rate of change at the intercept, and the quadratic parameter is interpreted as the rate of deceleration over time. Yeah, so the meaning of the parameters changes a little bit. One of the limitations of a latent basis model is that you can't extrapolate outside of the range of your measurements. So we can't say for NAPLAN what came before year 3, and we can't say what came after year 9. So we're really only looking within the parameters of those 4 repeated measures. But I think that's a limitation I'm happy to live with at the moment. Okay, I'll stop because it's nearly 9 o'clock. Any questions?
My goodness. Sally, that was so amazing. Can we just all just turn our microphone and give her a really amazing round of applause? Because I am floored at your ability to explain super complex stuff in a way that me coming and not knowing anything, I was with you the whole time. It was so great. The UNE students are lucky to have you. I'm so glad that you are sticking around to teach and keep doing research about these things. Thank you so much. I also really love your pedagogical method of using reproducibility as a way of teaching people to code, right? So I run a research internship at UNSW in psychology, where at the beginning of term, students come in knowing 0 R at all, but the problem that they need to solve over the term is, here's a paper that was published in Psychological Science, and we pick ones that have really funky GG plots. Your job, the data is open.
Yeah.
Your job is to work out how to make that plot from the data that you can download from the website.
Yeah.
And as a group, you problem solve your way, and what do I need to learn in order to produce this plot? Yeah. And so when you have a model in a paper and you can pull the data and reproduce what they've done, I think it's a really good way of learning. Yeah, thank you. So questions for Sally before we go? You're welcome to put your hand up or just turn your mic on and yell if anybody has questions. I have a question.
Yeah.
Oh, you go.
I was just going to say, with latent growth models, there's heaps more when you've got the data. Like, I have not shown anything about assumption testing or like data visualization or any of that stuff. So what I've shown is really just, here's how you code the model in. There's a lot of back work that has to go in before you get to that point.
Yeah, fair enough. I want to know what your next research question is.
Well, so one of the things I've been working on is multivariate models. So you can have latent growth models, which are like a base model, and then there's different ways you can incorporate more than one domain and look at like reciprocal growth processes. So yeah, so you can do things where you fit a growth model to 2 different domains, and then you take the residuals out of those 2 different domains and you see whether there are interrelationships between those residuals. So it's a bit hard to conceptualize. You're taking out because latent growth models are really between person parameters, but you can actually look at within person growth processes if you take out the residuals of those latent models. And so there's one called the autoregressive latent trajectory model with structured residuals. And then there are other ones. There's dual change score models. So there's different ways you can code in the change that's within person over time. So I'm looking at how you can model reading and spelling as co-developmental processes. Because they should be interrelated, but how they're interrelated is kind of like in specifically NAPLAN data, because I know it really well. How are they interrelated? How can we describe that?
That's interesting. So I wonder whether, so people talk about NAPLAN, no, people mostly don't talk about NAPLAN writing data.
Yeah.
Because I guess it's difficult, there's more measurement error, but you might predict the same thing with reading and writing, if you could measure writing in a way that was not hellish noisy, right?
Yeah, I don't like the writing data. I was an English teacher and I look at those writing tests and I'm like, I know they double mark them and they do put them onto the same scale, and they do all these fancy things with the test developments and stuff, but still I'm not quite sure what it's telling us. So
it comes down to measure. I mean, it doesn't matter what you're studying, it comes down to your ability to measure it in a way that's reliable and interpretable.
Absolutely. So I know, like I said before, I mean, people want structural equation models to be able to solve their measurement error problems. No.
You can perhaps disguise them like momentarily, but then So awesome. Thank you so much. Any other questions for Sally before we go? Oh, awesome. So you can follow her on Twitter. What's your handle again, Sally?
I think it's Sally Lars 27. I don't know.
Okay, something like that. I will tweet from Our Ladies the link to the recording on Our Ladies Global YouTube, tagging Sally. So if you want to follow her and see what she does with these amazing skills next,
it's really fun. Yes, and I hope that I can get more people excited about.
Absolutely.
In education research, because I find it really interesting. There's lots of data out there and lots of different and interesting questions that we can ask and answer. And
so what do your education students think? Do in the UNE education program, do they have to do this kind of quant-based stats modeling?
I don't think so no. So I've been in psychology for a long time, so there is a quant stats kind of track that you take in undergrad, and then there's an honours course that you take as well, but even then it only just touches on structural equation modelling. So I feel like there needs to be more, but also what's the potential of doing this and how you can fit your research question and your statistical analyses together. Because that was like an epiphany for me over time, where you learn about what's possible and then you go, oh, cool, because we can ask these research questions now.
And I think that's a bit of a failing of psychology research methods training, is that I feel like our students do so much research methods, but they barely get beyond multiple regression, and because there's just not enough time. And so their questions are kind of restricted to what you can test with a t-test and ANOVA or multiple regression. Which, I mean, they're okay, but this kind of answering this kind of question is much bigger. Yeah.
And it was one of those things where repeated measures, and everyone goes, oh yeah, repeated measures ANOVA. And I'm like, no. I've never liked repeated measures at ANOVAs. I don't understand them at all. They don't make sense to me.
The fact that they don't cope when you have missing data, it makes them almost useless to developmentalists, right? Because
absolutely.
Babies and kids never give you like perfect data, so you need to get that.
Yeah, absolutely.
Awesome. Thank you so much, Sally. This has been amazing. Everybody again, give a big round of applause. So good. We hope to see you at the next Ladies Sydney thing.
Now that I know about them, I'll come.
Now that you know about them, and there's a whole the pandemic sucks in that we haven't got back to in-person events. It's much funner to sit in a room with people. But the positive benefit of the pandemic is that everybody's recording events all over the world. And so you get access to not just Our Ladies Sydney, but Our Ladies New York and everywhere. So the Our Ladies Global YouTube channel is a wealth of learning resources. Where will the link to the recording be posted, Bernadette? I'm going to post it on the Our Ladies Global YouTube channel. So if you search on YouTube, Our Ladies Global, I'll post it sometime tomorrow once it downloads and then uploads. But there's all kinds of lots of Our Ladies chapters all across the world are recording. You have someone who wants you to go and tuck them in, so we should let you go.
Thank you. Thanks everyone.
a lot. See you, everybody.